Hey guys, how's it going? This is Ben from Chegg Tutors here, and today we'll be talking about the coefficient of determination. The coefficient of determination is a statistics term that describes a characteristic of a regression analysis. So, for when you have a set of X data and a set of corresponding Y data from the same subjects, and you want to know if they're linearly related. So the actual definition of this term is the proportion of variance in the dependent variable that is predictable from the independent variable. But what does this actually mean? A simpler way of thinking about this is that this coefficient of determination is going to describe to you what percentage of the variation in your y, or your dependent variable, can be predicted by or attributed to your independent variable. So, if you're watching this video, it's likely that you've already covered, or you're in a statistics course of some kind, and you've already covered what R is, or the correlation coefficient. So, R squared is related to R in many ways, but one main difference is that R squared ranges from 0 to 1 in potential values, whereas R, as you probably already know, ranges from -1 to 1. That's an important difference. You can't have a negative coefficient of determination, which, if you think about it, should make sense because this is R squared. So the way you find, one of the ways you can find R squared is you can take your R value, if you already have it, and just literally square it. So this lowercase r that you commonly see associated with correlation coefficient and this uppercase R doesn't mean that they're different things. You can just take the square of your R and you'll find R squared. Now, do note that R squared is commonly written as this with the superscript and not like this, or it's like R2 as an R2D2. And yeah, it's just hard to superscript things in the Chegg Tutors whiteboard interface. But moving on, let's look at an example for a coefficient of determination. So let's say we had a coefficient of determination, or R squared, of 0.64. So what does this mean to us? What does this mean to us if we get this out of like a linear regression analysis? Well, one way we can interpret this is that 64%, or 0.64, of the variation in our y variable, or dependent variable, can be explained by the independent variable, so our x. So this tells us that a decent chunk, around 60%, of our variation in our y can be attributed to our x. So it's pretty decent. That's a pretty high amount. So now that we kind of have an idea of what R squared is and what it denotes, let's move on to calculating it, which is probably the bigger deal for all of you watching this video. So I'm going to walk you guys through 3 ways of calculating a coefficient of determination given a given data set. The first way is going to be more math-based, and it's going to be for situations in which your professor or your teacher wants you to show your work, or if it's on a test and you're not given the easier methods I'm going to talk about to solve it. And the other 2 methods are going to be quick and easy, and they're going to be just if you want to find R squared really fast for some other kind of larger problem. Alright, so let's move on. So a little bit of review for most of you. So we're going to talk about what R is. So the correlation coefficient, or R, is also an output of a statistic analysis for a linear regression, and it describes the linear relationship between 2 variables. So this once again assumes that you're given a column of x, the independent variable, and a column of y, the dependent variable, and you want to find something out about it. So the first way that we actually calculate our R squared is to calculate our R, which should make sense, right? Because we already talked about that the R can just be squared to give us our R squared. It's that easy. But we have to calculate our R first in most cases. So let's look at an example problem down here. So here, let's say we've collected 5 samples of 5 students in your class. And the x's represent the number of hours they studied for the last exam, and the y represents the corresponding grade that person got on the test. So here we have 5 sets of data, right? So 1, 2, 3, 4, 5 people that you sampled. Okay, so let's say we have this data. So now how are we going to calculate our correlation coefficient, or R, from it? Because remember, once again, Right now we're going from the data to our R value and then to our R squared value finally. Well, we can look at this formula over here. So don't be intimidated. There are a lot of the values and there are a lot of summation signs, but I'm going to walk you through it, and it's pretty easy once you get the hang of it. So the n's represent the number of samples you have. So remember, we determined that our n is 5 because there are 5 sets of data. Make sure not to think that n actually means the number of different numbers you have in your table, because that would be 10. But remember that our values are paired. Each x is paired with a y, which corresponds to one person. So each person that you sample gives you a number of hours studied and a grade on the test. So n, remember, is equal to the number of samples you take, which in this case is 5. So if we look back to our formula, anytime we see an n, we're just going to plug in a 5 for it. Easy. So the summation signs are exactly what they usually are, representing in a math problem. You're just going to sum all the values of, in this case, over here on the left, the product of x and y. So if we look back to our data, that means you're just going to multiply each x by its corresponding y first. So x times 98, 2 times 74, 6 times 87, and then you're going to sum them, and whatever that sum is, you're going to plug it in over here. Now, you can see from the rest of this formula that there's a lot of summation involved, and it gets pretty tedious. And that's why I recommend, when you're tackling these kinds of problems where you need to calculate by hand, R, I recommend that you make one of these kinds of tables. So this table I made quickly in Excel, but you can do it by hand if you have a calculator, pretty easily too. But in Excel it's super easy because all you have to do is type in your x's, your y's, and you can use the summation function that's built into Excel to calculate the bottoms. And for the rest, you can just use formulas where you can say, these values are this column times this column, these values are this column squared, and these values are this column squared, etc. So yeah, the summations at the bottom make the problem a lot easier. So now whenever you need something to plug into your R formula, your correlation coefficient formula, you can just refer to this table. So let's do that. So here, up above, I've repasted the formula for R, and below, I show you which values you're going to plug in for those corresponding things in the formula. So if we look back, once again, the n is 5. We already said that. And for the summation of x and y products, we can look back to our table, our handy dandy table. We can go to the xy column and down to the summation, which is the last row, and we see that the value we're looking for is 1,926. So we go back to our formula, and we just plug it in. It's that easy. And then we do the exact same thing for everything else. Summation of x, no problem. We go to our table, look at x, go down to our last row, and it's 22. Plug it in. Same thing for y. So, it looks pretty easy now, but I want to point out one thing, and that's the difference between this value, which is the summation of all the x squares, and this value, which is the summation of all the x's and then squared. So at first glance they look pretty similar, but these two are in fact very different. The first one requires you to go to back to your table and go to the x squared column, and then go to the summation for 124. So that's what you would plug in here, and then a 5 next to it. So 5, 124, easy. On the other hand, for your let me fix this one sec. Right. So for your summation of x and then squared, since this summation of x is in parentheses, it's telling you to find the summation of x first and then square that value, rather than finding the summation of all the x squares. So for this value, we go to our table, we go to the x column, and we go to the summation, which is 22. And that's what we plug in first. But we haven't squared it yet, so we plugged in 22, and then we put a squared up top. So these two values will be very different, and it's important that you don't confuse them and put the same thing for both of them, because that'll give you a wrong answer. Okay, so here you can see all the corresponding values I plugged in for each value, and then using a calculator, or if pencil and paper is your thing, if you really love doing math and multiplication and division and all that, you do that too. But either way, you're going to simplify all these values, and you're going to end up with your R value for this data of 0.9909. So before we proceed on and calculate our R squared, I want to talk about a quick review of what this R value means, this correlation coefficient. So remember that R values go between -1 and 1, right? Which means it can't be outside those ranges. And do recall that anything greater than 0, R value greater than 0, means the linear relationship is positive, while any R less than 0 means the linear relationship is negative. So, depending on which course you're taking and what professor you have and what book they use, there are usually different arbitrary boundaries for what's considered a strong relationship or moderate or weak. So here I've used one that I just Googled, and it may vary, so don't use me as an absolute reference. Use your book or your professor. But generally there are 3 categories of strong, moderate, weak, and then sometimes they give this none or very weak category. And these values correspond to whatever you got. So remember, do recall that our value that we just got is 0.9909. So this is pretty high. This is close to that maximum 1 value that we talked about. So we look at our R value and see what category it falls into. And it turns out it falls between 1 and 0.5. So if we were asked to describe our correlation coefficient, we would say that it indicates a strong, positive, linear relationship between the number of hours studied and the grade on the test. So remember that the positive comes from the sign. There's no negative, so it's positive. And the strength comes from just this arbitrary category. But, I mean, since it's 0.9909, no matter what kind of source you use, it's probably going to tell you that it's either strong or a very strong positive relationship. So now that we've reviewed this, let's go on to actually solving for R squared. So after going through all this formula and math, you have your R. And luckily, the last step is pretty easy. Once again, we remind ourselves that our R squared can be found just by squaring our R value. And we'll do exactly that. We'll square our 0.9909, which gives us 0.9819. So this is our coefficient of determination. So what does this mean again? Let's apply it to the context of this problem. So this 0.9819 means that 98.19% of the variation in our y, or our dependent variable, which in this case, remember, is the grade that the student got on the test. So 98.19% of the variation of the grades can be explained by or attributed to how many hours they studied. Which should make sense, right? Because in this case, the relationship should be obvious. It should be immediately obvious to any of us college students or high school students who've taken a test, that usually the number of studies, the number of hours you study directly impacts the grade you get on the test. So it should make sense that a super high percentage of the variation in that grade can be explained by how many hours that the student studied. Okay, cool. So this was the first method of solving for your coefficient of determination. As you can see, it's kind of intensive. It uses a formula, a table, a lot of numbers, etc. And this is if your professor wants you to show work. So what if we're just looking for a quick and dirty R squared? Well, there are 2 ways I'm going to show you that you can achieve this. The first way is we're going to use Excel, and you're going to first type in your X and Y values over here. So I reproduced the X and Y values we just worked with on the left over here. Then you're going to highlight them as such, click Insert on the tab up top, and then go to the scatter plot symbol and click on the scatter plot. And it's going to give you something like this. Okay, so the next step is you're going to right click your data points, go to Add Trend Line, and it's going to give you this trend line, which is the least square regression line of these points, but we'll get into that in a different video. And make sure that on the right over here, under the Format Trendline options, you click on Display R squared value on chart. And there you have it. It's going to give us the R squared of this data of 0.9819. Should sound familiar because that's exactly what we got over here, except when we graphed this data, it was a lot faster. So once again, this is one of those super fast methods if you just want a quick R squared. So if you don't have Excel or you don't like using it, there's an even easier way you can do this. You can just go to Google and type in coefficient of determination calculator and click on the first link. It will take you to this website. And you can just plug in your x values here, separated by commas. So make sure that you type them in the same order that they're presented to you in this original chart over here. So 82642, 82642. And then you enter your y values. Make sure they're in the same order again. So 98, 74, 87, 82, 72. Yeah, we're good. So this is just to make sure that all the x values match up with their corresponding y values. And you just hit calculate. And it does your 5. Remember we said n is 5, so they agree with us. And it gives us your r, which is 0.99, and your r squared, which is 0.98195. So yeah, pretty close to what we got. Of course, when I calculated this by hand, I rounded along the values, which is why their answer of 0.98195 slightly deviates from ours, but it's pretty much the same. It's like to 4 places after the decimal point, identical. So yeah, these other two methods of using Excel and just using this a coefficient of determination calculator that you can just find online very easily are the super fast methods. But if you're looking to show your work, I would recommend you first solve for the correlation coefficient using this formula we just talked about, and then just square the value. And that's probably the method you'll be using on a test if the R isn't immediately given to you. Remember that if on a test or a quiz or homework, that if the R value is given to you by default by the problem, you can just square that and get the coefficient of determination. No need to go through all this mumbo jumbo. It's super easy. Just plug into your calculator, and there you have it. All right. So today we covered what the coefficient of determination is and how to calculate it, and we talked about a quick review of the correlation coefficient because it's so intertwined with what this R squared is. I hope everything made sense, and if you have any future statistics related questions, hit me up on Chegg Tutors. Yeah, so once again, I'm Ben with Chegg Tutors. See you guys around.